Everybody, I wanted to spend a little time talking about colligative properties, and in this video we're going to address vapor pressure lowering. When you have a solution that's pure, the balance between the particles jumping off in the vapor state and back into the liquid state is the solution's vapor pressure, is the solvent's vapor pressure. But when you have a solution that isn't pure, when there's something dissolved in it, the vapor pressure will always be lower. And so that pressure is lowered by how much proportionally solvent, or how much solute and solvent there is in relation to each other. And so you have a formula that looks kind of like this. And so this is the new vapor pressure, and this is the vapor pressure, the original vapor pressure of the solvent, or the one that you can look up. And remember, there are tables of all of this stuff. Okay, so if we have tables, we can look up what the vapor pressure is at certain things. And this guy here is the mole fraction. Okay, and so if we know how much of the solvent is there compared to the whole solution, then we can also find out what its vapor pressure is. And so this is kind of the chemistry behind this. And so when you have vapor pressure, the amount of the vapor pressure is the pressure the molecules are applying, jumping off into the vapor state from the liquid state. And so that happens at a certain amount and applies a pressure. Okay, and typically the atmospheric pressure is in equilibrium or is in balance with the vapor pressure that's acting this way. Now, when you add a solute to the solution, when you add a solute to the solvent, that interaction between the particles is preventing them to jump into the vapor state. They are not as likely to jump out into the vapor state because of intermolecular forces, attraction that's going on between all of these things. So the vapor pressure is going to be inherently lower for things that dissolve because they are more attracted to the particles of the solvent, and the solvent is more attracted to the particles of the solute than it is to be likely to jump into the vapor state. Some molecules of solvent jump into the vapor state, but just not as much. So let's talk a little bit about, or let's go through a sample problem of how much, what vapor pressure lowering is going to be, or what the effect of this is going to be. And so we have antifreeze, which is ethylene glycol, and that is dissolved in 1.5 kilograms of water. So it's like we're winterizing our cars. Okay, you put antifreeze in the radiator of the car, and so what we want to do is we want to find out what the new vapor pressure of the water is going to be when it's at 90 degrees C. And so that new vapor pressure of the solvent is going to be equal to the mole fraction. It's a capital X, or this funny X, times the known vapor pressure. And so we say assume ideality because we just have to assume that these gases and liquids are behaving as ideally as possible, so that way we don't have to get into all the crazy considerations that are going on. So basically we want to calculate mole fraction of water. So in order to do that, we need to know how many moles of antifreeze, how many moles of water there is, and then add them together and then find out how much water there is. So I have my calculator up, and let's start by doing that. Okay, so mole fraction is equal to moles of water over the total number of moles, which in this case is moles of water plus the moles of ethylene glycol. And so I'm gonna put AF, antifreeze. Okay, so now we have to do some math to convert. So moles of water, so we have 1.5 kilograms of water. That equals or goes to 1,500 grams of water. And now we convert that to moles, so it's grams on the bottom, moles on top. 1 mole of water has a mass of 18 grams, so 15 up. Okay, so 1,500 divided by 18, that equals 83. As my voice cracks, 83.3 repeating moles. And now for ethylene glycol, we have 651 grams. We're going to X-line that, grams on the bottom, moles on the top. Every 1 mole, now we have to figure out the molar mass. Hydrogen, there's 1, 3, 5, 6, so that's 6 times approximately 1. Oxygen, there's 2 times just approximately 16. And carbon, there's 2 times approximately 12. So 2 times 12 plus 2 times 16 plus 6 times 1. And so we get 62. So this is 62 grams is equal to 1 mole. So 651 divided by 62. And so this is 10.5 moles. So the mole fraction of water equals 83.3 repeating over 83.3 plus 10.5. So let's do it this way. Yeah, we'll do 83.3 divided by, and I'm going to put this in parentheses, 83.3 plus 10.5. Okay. And so that's a mole fraction of 0.888. Okay? So 88.8% of this solution is water. So now all we need to do is find what the vapor pressure of water is at 90 degrees, and we can use a table to do that. Okay, so I'm going to go back through some of these slides, and so I know that I have the vapor pressure at 80 degrees. Let's see, 80 degrees. I'll move my calculator out of the way here. Okay, so at 80 degrees, the vapor pressure, oh, it was 90 degrees, I'm sorry. At 90 degrees, the vapor pressure was 525.8. Okay, so let's, okay, so 525.8. So we will go to slide 11. Okay, so now I'm going to make a little room. So I'm going to get rid of this. Okay, get rid of this. And I'm going to say that the new pressure is equal to 0.888 times 525.8, and that pressure is, so that is equal to, and so I'm just going to take that answer, and I'm going to multiply by, let's see here, times 525.8, and that answer is 466.9, and that's the new vapor pressure, and that was measured in millimeters of mercury. Okay, we can always convert those to torr or atmospheres or whatever you want, but we need to make sure that this unit is the same as this unit. Okay, so let's keep going. So so now we're going to make a cup of coffee. Okay, that's the same idea. Okay, so here we're going to put sugar into 225 grams of coffee, 10 grams of sugar. Now we want to know what have we changed the vapor pressure? Okay, how much have we changed the vapor pressure by? Okay, well, again, the new pressure is equal to the mole fraction times the pressure of the pure liquid, the vapor pressure of the pure liquid. So again, we have to do some conversions. So we have to get these in moles. So we'll do water first. Water is a little easier than sugar. because most of us by now know what the molar mass of water is, but it's 225 grams, the X line, grams on the bottom, moles on the top. For every 1 mole is equal to 18 grams. And so this is going to be 225 divided by 18, and that answer is 12.5. So that's 12.5 moles. Now, sucrose has a molar mass difference, so we're going to have to do some molar mass calculations, so grams per mole. And so this is, let's see, so this is going to be, C is 11 times about the 12, about the molar mass of carbon, and this is going to be 22 times about 1, and oxygen is going to be 11 times about 16. Okay, so 11 times 12 plus 22 times 1. You don't have to put the times 1 in there, but I am doing it just to show completeness. Okay, and then we're going to add 11 times 16. Okay, and so the molar mass is 330. So 1 mole, 330 grams, and so 10 divided by 330. Okay, so now we have 0.0303 moles. Okay, so the mole fraction of this, or sorry, the total moles, the mole fraction, right? So the mole fraction is equal to 12.5, the moles of water, over 12.5 plus the moles of sugar. Okay, so that plus 12.5, so that's our total number of moles, and 12.5 divided by the total number of moles, and so this is equal to 0.998. Okay, so that's the mole fraction. So now, again, we're going to have to go to and look up what our vapor pressure is. Let's go to here. Okay, now we want for 60 degrees. 60 degrees, the vapor pressure is 149.4. 149.4. So we're going to go here. We go here. We're going to go to slide. We're going to go to the last slide. There we go. So this is going to be, for this problem, this is going to be 0.998 times, and then the vapor pressure, 149 point, of course I forgot, right? Go to slide, we go there, we go back, 149.4. Okay, good. Okay, go to slide, good. Okay, 149.4. And so 99.8% of that, so we go 0.998, which is 99.8% times 149.4. And so our new vapor pressure really hasn't changed much, 149.0. And so what does that mean? And okay, so that's still millimeters of mercury. So because this hasn't changed much, that means it's still going to be like, you're going to still smell it just about as much. You're still going to it's still roughly going to have the same boiling point. So I mean, there's lots of boiling point. So there's lots of things that happen here. So so there's a couple of cases. Okay, one where the vapor pressure changes a bunch, and one where vapor pressure doesn't change a whole lot. Okay, so that is the colligative property of vapor pressure lowering, and have a great day.